let us continue with this these lifting results. So we have lambda ring and I an nilpotent, an ideal. Actually, we have reduced such that I square is 0. And so we set S spec of lambda, and it contains S naught spec. And of course, the two have the same topological space, since we have an nilpotent ideal. And so let G be a smooth affine S Grupski, smooth affine. And so let denote by A. So it's Hopf algebra. And let Y be S group C. So what we require that it is flat over S and such that the base changed and such that Y0 is multiplicative type over the 0. Okay, and we want to study this question of lifting. And so recall, so denote by G plus as a group functor, such that for any scheme T over S, G plus of T is equal to G of T base change to S0. Okay, so let's think a little bit about this. So say T is the spectrum of some ring R. So what is the point? So here we have the algebra A, and okay, so we have the quotient A over IA. No, flat suffices. Yeah, flat. And okay, so here we have R over IR. Okay, so so actually, what I want to say is that G of T0 is the same as G0 of T0, because a point here is just a morphism of algebras like this. But since the image of I is 0 here, of course, this is such a morphism factorizes like this. Okay, so the maps, so okay, these are two things. But now, so G plus is a different thing. It's so if we have R, so given with its projection, so to every ring A, it associates a morphism from A to I. over IR. So let's call this, probably I want to call this phi. And so okay, so we have this. And of course, if we have a morphism from A to R, it induces one like that. And so we have, hence, we have an exact sequence of group pointers. So J sits in the middle, and it goes to J plus. And so on any T points, it is just, so there is the induced map like this. And so this map is always surjective. So this is surjective for any T because J is smooth. Any since J is smooth, any infinite, well, any points lift to here. So this is surjective. So this means that this morphism of group functors is surjective. And let call it pi. And its kernel we denote it by L of G prime. Okay, so this is just a definition. So L prime G is just the kernel of the natural map from G to G plus. Okay. So why is there a prime here? Because in SGA3, de Mazur considers a more general case where G is not a group, where one has just a scheme and a map from X plus. And then it defines an object Lx, which is the same as before. So that, well, so Lx is a functor of X plus. That is, if you have a map so what is this? I'm confused. So what was this? So this was a map. This was a map from T to G. Yeah. So this corresponds to the lifts of a given map at the of a lambda 0, and then there is a kernel here. Okay. Well, it's not a group, but if there is something like a unit section, so there is something here, and this explains the prime, because in general there is a bigger object here. But so this need not concern us. So we adjust this definition. Okay, and so we saw last time. So last time. No, not at all. No. L is for Lie. Yes, that's. Well, it's something like the Lie algebra, rather. Hmm? Okay, so uh, yes, this L prime is like the Lie algebra. Okay, actually, so last talk we saw that if T is a spectrum of some ring B, then this functor evaluated at spec B is naturally isomorphic with a set of algebra homomorphism from A to B of the form. So there's the augmentation map plus plus from lambda 0 into IB. Where M is the kernel of the augmentation map from lambda, and M0 is obtained by base change, okay? And so I denote by F of spec B the lambda 0 module which is here. So this is from, yeah. Yeah, epsilon plus from this, because so this L prime, so let me write B instead of spec B. So this is a set of algebra homomorphism psi going from A to B such that the composition such that this diagram commutes. Because it's in the kernel. So this means that the reduction of phi modulo I is a unit unit map. And so this means that it factorizes like this. Okay, and so since B is a lambda algebra, I identify epsilon as a morphism of A into B. And so the claim is that this is the set of psi, which are of the form epsilon plus D with D in this module, which I denoted by F of B. Okay. So we have a. So if we forget about the epsilon, so we have a bijection. So we have a bijection between the kernel and this lambda 0 module. And I proved and so this bijection transforms the group law here, the group law here of, well, so this is a normal subgroup of G of B. So it comes with a group law, and so here we have this addition, the addition coming from lambda 0 module structure. Okay, so I finished the last lecture with the computation showing that well, exactly the well, so such a homomorphism is a group, well, is an element in the group G of B, and we if we make the so basically, so this statement is that if we take one such element and we call it like this, and if we multiply it with another one, and the multiplication being the group law inside this group, so the result is just epsilon plus D1 plus D2. Okay. And so it transforms this group law into addition here. And it transforms the conjugation action of the group G of B. So again, we have a normal subgroup. So G of B acts by conjugation, and it transforms it to the action of G of B on the module f of B, coming from the so-called co-adjoint action of G0 on M0 over M0 squared. Okay, because so the group G0 acts on itself by inner automorphism. And so it acts on the algebra function, which is A0. And the conjugation action stabilizes the unit section. And so certainly the action on the algebra function stabilizes the kernel M0 of the augmentation map. So we have a G0 action on this lambda 0 module by algebra automorphism. So it induces an action on this quotient, which we call the co-adjoint action. Because the dual of this one is the Lie algebra, and the resulting action on the dual is the usual adjoint action. Okay, so we have a okay, so here we have a lambda 0 module with an action of the group G0. And the nice thing is that it is the same as a group law and conjugation action of this exact sequence. Okay. And now take so we were taking T arbitrary. So let's take the Y given in the okay. So this is a flat group scheme such that Y0 is of multiplicative type over S0. And so again, B, okay, so B is a ring corresponding to Y. And let phi So suppose that we are given a morphism from Y0 to G0 be given. That is, we be a morphism of S0 group schemes. And we can view this, view it as a morphism of S group functors, which I still call phi, but going to G plus. Because, well, that's exactly the definition of G plus. A morphism from T to G plus, by definition, is a morphism from T to G0. And of course, giving a morphism, any morphism from, well, any morphism from T to G0 factors like this. So, okay, so we apply this to Y. Okay, so we are given a morphism here, and we view this as a morphism from Y to this strange functor. And we pull back. So we form the fiber product. So we call E the fiber product of our group G over G plus with Y. Okay, so we have the natural map phi here. So this is a fiber product given by the map phi on the one hand and phi on the other hand. So we can form this this object, and we pull back. So we pull back this short exact sequence, call it with a star. So we pull back using this phi. And so we get a short exact sequence where we have so Y. So instead of I would say that L prime of G is the same as this functor F. So I write here F. And here I have this E. And well, let me write it the both exact sequences. So this is the original one. And so we obtain a new one. So we have here this G. So here we take the identity map. So here there is a natural projection from E to G. And here's a projection to Y. And here we have the map phi. Okay. And F is the obvious map. Okay, and F goes into E by the inclusion F inside G, and the unit map F goes to the trivial group into Y. Okay, so if we define the map like that, so we have we obtain another exact sequences, and okay, and so now we are almost done. So since G is smooth, phi regarded this time as a map from y to what do I notice? Yeah. Hmm? Because yeah, because we are going to compute the cohomology of y with values in f, and this we can do because the L prime of G at the beginning was rather mysterious, but well, because so this is a quasi-coherent module of y0, and so this is we are going to go well. We will see in 1 minute that we can compute its cohomology and it is 0. Because so this is a rather mysterious object at the beginning, and so this is a big step to replace this unknown object by this more manageable one. Okay. Okay, so if we so this is smooth, and so we have this map phi that we can view as a map from y0 into G. But since this is smooth, since G is smooth, this map lifts to a morphism of schemes S from Y to G. Okay, so this is given by smoothness because okay, because Y is in an infinitesimal neighborhood of Y0, and so by smoothness of G, we have that there exists a map of scheme. Okay, and so here we add this projection pi, and so let us denote by pi sub phi the map here, and so we have the section here S, and so let's call it here. Let's call this map the first projection. Okay, and so one has the following easy observation. That there is a bijection, so there exists there is a bijection from the set of morphisms of schemes tau from Y to E such that the composition is the identity of Y. And so the bijection sends such a tau to tau composed. So if we have a tau like this and we compose it, so this is, so we have a bijection with morphisms of schemes, psi, from Y to G lifting the given phi from Y0 to G0. And so this bijection also induce a bijection from the subset of morphism of group schemes. And here the same thing, so morphism of group schemes of group scheme, so phi from Y to G lifting phi. Okay, so what we are interested in is finding a S like that, which is a morphism of group. And by this is the observation. This is the same as finding a section. This is the same as finding a section, a group morphism, which is a section of this. Well, and well, so actually the map in the, well, yes, yes, yeah. Yeah, that this is a bijection is clear because well, if you have a map from Y to G and well, you just take the identity map on the second factor, and so you have a map. Okay, and so S also defines a set. Well, so I can also view S as a section here as a scheme. And the question is whether we can modify S to get a morphism of group scheme. Okay, and by what we saw the other day, so S defines an element in F of Y square, which is, so F is a functor of, with values in abelian group and so in G0 modules, which is 2 per cycle. Okay, this is the computation we did the other day. So as we can say that the computation works in, well, they work in an arbitrary category, or they work in the category of schemes, because to find a section, a group theoretic section, well, if we work over arbitrary T points, this is the same as finding a section, a group section which is functorial in T, and so there is an obstruction which is in the group cohomology, and yeah. no. So this is, I'm saying that this observation is easy. And so I translate the original problem, which is finding a group homomorphism in that direction is the same as finding a section of this extension. And then finding a section, so we have we know that there exists a section which is a scheme map. Yeah. But we know that the obstruction to modify it to a section of group scheme lies in some group in the set of morphism of y cross y into F. And now we use a second hypothesis since now we note, so an important remark, if P is a flat lambda algebra, then this F of B, which by definition is from, let me, then, so actually what is the ideal IB of B? It is the image of, well, it is the image of B tensored lambda over I. And if B is flat, so this is an isomorphism. The natural map is an isomorphism. And so this is all since I is annihilated. Okay, so this is since I square is 0. So the nice thing is that if B is flat, we have this, and hence F of B. So this is from lambda 0 of M0 over M0 squares with values in IB. So this is from lambda 0 with value in I, 10 thirds of the lambda with B0. And furthermore, so this is the same as and so this is the same because this one is a locally free. This one is a locally free or finite rank module. And so if we tensor by something which is flat over lambda 0, so we can take this one out of the tensor product. Okay. And okay, so I think that I've used all hypotheses. Okay, so the conclusion is that on the subcategory of, so I put here just fine, this is just for my convenience, but on the subcategory of flat lambda schemes, well, I can on the category of flat lambda scheme, the functor which sends a scheme T to L prime G of T, so which is the same as F of T, coincides with the nicer functor, which sends T to the module from. So let us give a name once and for all to this module. So let's call this lambda 0. So this is a lambda 0 module. So it coincides with the the nicer functor. We just take this and we tensor over lambda 0 with the ring of function of T0. Okay. Well, which is, well, so which is the functor. Well, which is what it is. Okay. So this functor is so this functor is defined by the lambda 0 module L0. Okay, so now, so our group scheme Y is flat over S, which is spec lambda, and so is this one, and so we get, a 2 cocycle in f of we get a 2 cocycle in this functor. Well, yes, okay. So what is this? So this is L0 tensored over lambda 0 with the ring of Y, which I call B0. Okay, so we get an element in this Okay, so finally, the abstraction to lift the given morphism to a morphism of group schemes from Y to G. So lives is an element of this tensor product, L0 tensor B0 tensor B0. And the fact that it is a cocycle is that if we look at the map here, with an element in there whose image here is 0. Because the condition that it is a cocycle is written by this, well, some explicit formula. And so this says that the image of this element in this triple tensor product is 0. Okay, so that is thus it is an element of the partial cohomology group of the group Y0 with values in the module L0. And this is 0. And this is 0 since Y0 is multiplicative, is an empty group over S0. Okay? So this answers the questions of Professor Balaji before. So the abstraction lives in, well, in some strange looking kernel. And so we compute the kernel and we obtain that it is given by a functor from schemes into lambda 0 module with some group action of Y0. And if further Y0 is flat, the functor is well, see, what we get is even nicer. It's given by this module, and the obstruction lives in some cohomology group, which we know is 0. So the map lifts, and so yes, it lifts, and we want to control also what are the possible liftings, and further. So the group cohomology discussion of the other lecture, the group cohomology discussion shows that the set of all group homomorphism liftings of phi to all group homomorphism lifting, let me call them psi, so from Y to G. So all group homomorphism psi from Y to G lifting the given phi 0, lifting the given one. So we are talking about morphism here psi, and if we mod this out by inner automorphism coming from the kernel, inner automorphism from kernel of pi. Okay, so well, so if we have an element G in the kernel of pi, and if we conjugate a lifting, well, so this is still another lifting, okay? And so if we decide that two liftings are equivalent if they differ only by conjugation by an element in the kernel, so the set of equivalence classes of this, so we saw previously that this one is in bijection with the H1 of the group Y0 with value in the functor, so this is 0. And so this is also 0. And so this is exactly what we wanted. And so let me write the theorem that we have obtained. And so we have proved. And so we have proved the theorem. Okay, so in my notes, it was, what was this? So in my notes, it was the proposition. So let us change notation slightly, and let us denote by U0 the given morphism. Of group schemes over S0. Yep. Yep. Yes. It's the coadjuvant action on the first factor. Yeah. So this yeah. Yes. Yeah. This is this is going to come. But actually, yeah. So this will be a special case. But for the moment, we work with a group which is only assumed to be affine and smooth because we want to apply this to the case of a reductive group. And so the main theorem that we want to prove is that there exists maximal tori inside a reductive group. And so the proof is, well, we pick a closed point. So we have a reductive group of a field. There is a maximal torus T0. And applying this technique, we are going to lift it. So we yeah. So this is why here G0 need not be of multiplicative type, but in our mind it will be reductive. Okay. So the first statement is that there exists a lifting of U0 to a morphism of group schemes U from Y to G. And secondly, if V is another such lifting, then there exists an element G in G of S, but not only in G of S, an element of G of S with image by reduction mod I is the identity, such that V is the inner automorphism defined by G. Okay, so this is exactly the theorem that the proposition that we needed to prove. And I write it explicitly because, well, when one sees this, well, what does this mean, modulo inner automorphism coming from the kernel of pi? So this is rather abstract. But when we write it like that, then we really see the meaning that any two such lifting are conjugated by an infinitesimal point. That is an element of G which reduces to the identity in 0. Okay, and so this is a very important result that we are going to use now. Okay, so let us keep this, and now let us derive some consequences. Okay, so just for a while, let us be, so let's start a new chapter, a new section, and with the following proposition. So we have S a scheme containing a closed subscheme. S0 with the same underlying space. Well, so actually, things to this as S as spec of some ring lambda, and S0 is a spec of lambda over I and I important. Okay, so so firstly, as a functor which takes a group H to its phase change to S0 from the category of groups of multiplicative types over S to the corresponding category over S0 is, well, you expect me to write is an equivalence. Well, be patient. So we will prove first that it is fully faithful. Okay, so it induces bijection on morphism. And secondly, it induces an equivalence between subcategories, between the subcategories of quasi-isotrivial, respectively, isotrivial empty groups. Okay. So I open here a parenthesis because I'm really struck by Grothendieck ways of thinking, because at the very end, he's going to prove that any empty group is quasi-trivial. So what would a normal mathematician do? At least what would I try to do with such success is to start by proving that every empty group is isotrivial, is quasi-isotrivial, which is probably a hopeless task. So what does Grothendieck do? Probably he thinks that, well, if the result is true, then the subcategory of quasi-isotrivial groups must have all the properties of the category of all groups. So he begins by studying the small subcategory, and he derives nice properties of it. And at the very end, he proves that it coincides with the category of all empty groups. So I think it's important to emphasize that, because we are going to see many results that are true under the quasi-isotrivial hypothesis. And you will see it is really used in the proof. And at the very end, by some bootstrapping, he has proved so many results about quasi-isotrivial empty groups that he proves that any empty group is quasi-isotrivial. But this is very far from obvious. So for the moment, we have to accept that in every proposition or theorem, there is an hypothesis like that. Okay, and only at the very end, well, we see, well, we will discover that this is not necessary, but this is highly non-trivial. Okay, so let's prove this, this nice proposition. So proof of one. So assume first, assume, okay, so what we must prove, so let H and G be empty groups over S. So we want to prove the natural map from S groups. So how did I write it? From H to G to S0 from H0 to G0 is bijective. Okay, so this is the map induced by base change. Okay, so assume first that G and H are diagonalizable. That is that G is given by some abelian group M, and H is given by some abelian group S. Yep. No, G is not multiplicative here. Here, yes. Ah. Yeah. Yes. So so this proof. Yes, I think you are. I think that you are right. Okay. Mm-hmm. Oh yes, you're right. So I can. Okay, so you're absolutely right. So we can use this. So the first point says that the map is surjective because anything lives, and so this says that the map is bijective because two liftings differ by conjugation, but since G is commutative because it's a group of multiplicative type, so this ensures that the same. Okay, so thank you. So this is okay. So good. So this is a nice shortcut. So so one follows from a proposition. Okay, that's nice. Okay, so I was going to give another proof, but which is completely irrelevant because the hypotheses here are slightly more general because, well, the same underlying space means that this is just a nil ideal. So it's a base. So any element of the ideal has some power which is 0, and so if lambda is not noetherian, the ideal is not necessarily noetherian. But this is a subtlety that we don't need because well, okay, so if we take the special case, so this is slightly less general that the result proved by Grothendieck, but it suffices for our purposes. And okay, so we have this. And so we just have to prove the second part. Okay, so let H0 be a multiplicative type group over S0. And so we want to lift it. Hmm? No, not even that. Yes. No. I wrote this just to make the connection with the previous results. And so actually the proof that I was about to give is purely topological, because at the very end, one has to consider locally constant functions from S to M or N or something like this, and S and F0 have the same topological space, so the result is true. So in a sense, this is more general, but the extra generality, we don't need it. Here, yes. No, but yes, under unique hypothesis, I think we can reduce to S affine, because we cover S by affine pieces, and it's enough to prove that over each affine piece there is a unique lifting, and so I think it works. Okay, but again, in the very end, we are going to apply this to the case where S is a local ring. So it's enough to do the case where S is affine. But so yeah, but I think that with a uniqueness property, we can reduce to the affine case. Okay, so now let's prove that it lifts. So want to prove. So we want to find H empty group over S such that H reduces to this one. And so by hypothesis, H naught is quasi isotrivial. Hence, there exists a map from S prime 0 to S0 such that if we base change H0, so this is some group of multiplicative type of this. Okay, and this map is etale. And so this one sits inside S. And we use that they have the same topological space. And so we use that base change, x going to x is an equivalence between schemes etale over S and schemes etale over S0, because S and S0 have the same topological space. And so So this etale map comes from an, so it comes, so there exists the first line, and it comes from, okay, so we can complete the square lines act with a map which is etale. Yes, thank you. Okay, and so what we just set H prime. So when the group is D of M, of course we can lift it. So we can do this. Okay. And of course, this H prime, so this is the H prime 0 that we have. But so how is this one defined? Okay, so this one, so this is the given H0, and we base change over S0 to S prime 0, and it turns out to be isomorphic to this. Okay, but so since H prime 0 comes from H0 by base change, it has this datum which is an isomorphism. Ah. So it has an isomorphism like that, satisfying the cycle condition. But by faithful flatness, by one applied to the base change from S prime 0, this descent datum comes from a descent datum on H prime, which is just this relative to S prime to S. Okay, because so here we have some descent datum, and so this one lives here, and it reduces to the other one, and so by since the reduction map is fully faithful, using this for the reduction from S prime to S prime 0, so we obtain a descent datum here. And H prime is affine over S prime, and so the descent datum is effective. And hence, there exists a S group H such that H prime is obtained by base change. And And so this H prime is a diagonalizable group, and so H is automatically is an empty group, and it is automatically quasi isotrivial because it is split. It is split by this map, which is etale. Okay, and it remains to prove that it reduces okay. So it remains to see that need to prove that is isomorphic to the H0 we started with. But going to S prime 0, this is true. Because H okay, because H cross S prime 0, so this is the same as H cross S prime cross H prime 0. So this is D of M S prime 0, and this is precisely isomorphic to H naught cross S0, S0 prime. Okay, and so this morphism is etale, hence it is a morphism of descent. And so the isomorphism between the base change, so the isomorphism between this one and this one comes from the base. Hence morphism of descent. Okay, so this means that so it's a morphism of descent, so this means that we have this equality. Okay, and since here, well, and also in the other way, so here there are isomorphic, so actually they are already isomorphic. Okay, so this proves the result under this quasi-isotrivial hypothesis. And you see that the key point is that any etale map here comes from an etale map here. And the same proof works. So isotrivial, the proof is exactly the same. Simply, this means that we can take a map which is etale finite, and then also this leads to etale finite. Okay, so we have this in both cases that. So this map is an equivalence of category, provided that we restrict ourselves to the groups which are quasi-isotrivial, or the smaller category of isotrivial ones. Okay, so no, this is the next statement. Yes, there is a unique isotrivial. So if let's say H0 is isotrivial, so this proves that there is a unique isotrivial H which lifts it. The next result that I'm not, the next result is that actually if H0 is isotrivial, then any group of any empty group that lift H0 is actually isotrivial. And so this is a slightly stronger result, which is in the note, but I'm not going to write it because I want to go to complete noetherian ring. Okay, so the first step was infinitesimal thickenings. So going from, so S and S naught have the same topological space. And so basically we know that we can lift everything from S naught to S. So now the next step is to go complete. And so now the idea, so let a complete noetherian local ring S spec A contains S0 spec of A over N. Okay, so we want to extend our previous result to this more general case. Okay, so now they do not have the same topological space, but well, still, if the ring is complete local, we are going to see that we can lift. Okay, but we need an intermediate result. Which is called the, well, so let me just write a nice lemma of Grothendieck. And we will see, so A, a noetherian ring, M, a set, and A, M, M prime, for M, M prime in the product. So this is a family of elements. So this is an element in the product of n times m copy of A, our family, such that firstly, well, actually the family is supported on the diagonal, and secondly, there exists a finite number of elements bi and di in an. So let's say I is running from 1 to n, such that for all m and m prime, one has the equality m, and this is the sum for I equal 1 to m of the products bi m ci m prime. And then the conclusion that then the supports of family is finite. Then the diagonal terms are 0 for all but a finite number of M. Okay, so this looks very mysterious, but so what this says is that so consider this. So consider this product of copies of A, and we consider there is a natural map from this larger ring here. And we have a family here, MM prime. So okay, so maybe I don't know. So let's call theta this natural. So the second point is that so this family lies in the image of theta, and so assumption 2 is this, and the other one is that this is 0 if M is distinct from M prime. Okay, so the conclusion is that actually the family of non-zeros AMs is finite. Okay, so maybe I will prove this later, but I should explain why this is needed. Okay, because so this is going to appear in the following theorem. 19.3. So let's A Noetherian ring with an ideal I such that the natural map from A to the projective limits of this is bijective. Okay, so this is the case if we have a complete, noetherian complete local ring. And that S be the spectrum of A. And so this contains Sn, which is a spectrum A over In plus 1. And now let G be a fine S group scheme. And H isotrivial empty group over S. And of course, we denote by Gn, Hn, their pullbacks to Sn. And then the theorem is that so the first part of the theorem is that the canonical map okay, so if we have a morphism of S group schemes from H into G, well, of course, by reduction, it gives a morphism between the reduce and this. So this is and so this gives So we have a morphism like this. So any morphism gives rise to a compatible family of morphism between the reduction. And the point is that the canonical map is adjective. So, which is, well, and so let me show you that this follows from the, so this is highly non-trivial. And this follows from the previous lemma. Okay, so assume first that H is so the ring of function. So this is just the group algebra A of n. Okay, and set. How do I want to call the other one? And so let's call this B. And let's see is a ring of function of G. Okay, and so let's delta H, delta G be the multiplication map. And also, so let's EM or M in M. So let this be the canonical basis. Canonical basis of B over A. Okay, and also consider the completion. So set B at. So this is a projective limit of B over IN plus 1 B. Same thing with this one. Okay, so one can note first that the map from B to its completion is injective. Because what is this? So this identifies with the families AM, M in M, and A to the M, such that for any N, all AM but a finite number in IN plus 1. Okay, so the completion of this group algebra, well, it's they are the families that tend to 0 with respect to the I-adic topology. And so the difficult part is to prove that this map is surjective. Okay, so let's okay, so let phi n be a projective system of algebra morphisms. CM to RBM. And so this gives rise to okay, so I'm just going to write a commutative diagram, and then we will finish tomorrow. So we have the map, the canonical map going to this one. And here we have a map which is induced by the so this systems here, so this leads to a map here. And so here we have the comultiplication map, which goes to C of C. And here there is a map that goes to B tends to A, B, subcompletion. And so there is a map here which is obtained by completion. And so so we are going to prove tomorrow so that this composite, which I called capital phi, so the claim is that phi of C is actually contained in B. And so this uses the lemma. And actually, this is the key point in the proof of the algebration theorem. Okay, because so we leave, but actually this goes into B, not outside B in the completion. And so actually we obtain a morphism of algebras. And so the proof relies on the lemma, so we will finish this tomorrow. Okay, thank you.